The tides, familiar to everyone at the seashore, are really generated far out to sea in the deep ocean. As the Earth turns under the gravitational pull of the Moon, the ocean water on the side nearer the Moon is drawn towards it by a small excess of gravity, while the ocean water on the other side is drawn away from the Moon by the centrifugal force of the orbit. If the Earth turned slowly enough, the water would pile up into two broad heaps, one centered here and one centered here. But the speed of rotation of the Earth prevents anything as simple as this happening, and instead, the tides sweep around the oceans in a complicated pattern of waves, thousands of miles apart. This map gives a rough impression how the crest of these waves progress, repeating themselves every 12 hours, 25 minutes. Really very little is known about these waves, and oceanographers are only now beginning to tackle the very difficult problems involved in determining them, using modern techniques such as the computer, and also by direct measurements with instruments. In a recent international exercise, most of the instruments which have been built for oceanic tide recording were compared in close proximity in the northern part of the Bay of Biscay. To record tides in the open sea, a capsule is lowered to the seabed and left there to record the variations in pressure caused by the rise and fall of the sea surface. This tidal pressure capsule was developed by Frank Snodgrass at the University of California and is here being prepared for its descent. The two spheres contain most of the recording equipment and are strong enough to withstand pressures up to 1 ton per square centimeter, and buoyant enough to float the capsule without ballast. The lower part of the heavy metal frame provides the ballast weight to make the capsule sink to the bottom of the ocean. For the first few hours, the capsule transmits acoustic signals through the water, which enables the scientist on board ship to check that it is functioning correctly. If so, it is left for a month to record internally. When the ship returns, coded acoustic signals are transmitted to instruct the capsule to release ballast and float up to the surface. At the surface, the capsule starts to transmit radio signals to aid recovery. But finally, eyesight and seamanship are needed to bring it safely back on board. In the shipboard laboratory, the spheres are opened up for inspection. They contain miniaturized computer circuits for interpreting the data received from special quartz crystal sensors in terms of tidal variations of pressure, temperature, and water velocity. The data are recorded on a magnetic tape at intervals, controlled by a crystal clock. This instrument is sensitive to 1 centimeter change of sea level in 6 kilometers depth, and so has to maintain an accuracy of 1 part in a million. Similar in principle, though less elaborate, is the capsule developed at the Wormley laboratories of the Institute of Oceanographic Sciences. This capsule is designed for use in depths up to 200 meters and measures the tides using a strain gauge pressure sensor. The acoustic signals in this case do not transmit tidal data to the ship, but are used to locate and release the capsule from the seabed using a pyro release, which is positioned between the ballast weight anchor and the main frame. The capsule is lowered from the ship to within 10 meters of the seabed, when it is released to free fall onto the bottom. Returning to the site a month later, transmitted signals from the ship switch on the capsule's acoustic beacon. This beacon is used to maneuver closer to the capsule position before the ballast is released. The jelly-like objects attached to the rope are squid's eggs. To aid recovery, with the capsule at the surface, an auxiliary spherical acoustic beacon operates, and this can be detected on the ship using hydrophones. Thus, in poor visibility, the capsule can be located. Yet another variation of design is the capsule developed by the United States National Oceanographic and Atmospheric Administration. It uses a large, heavy framework to keep the recording mechanism, a delicate optical system, horizontal. The pressure sensor is a bourdon tube. A syntactic foam cylindrical float gives independent buoyancy and is launched first of all. Then the main framework, most of which is ballast, including a train wheel at the center, is carefully lowered onto the seabed. Hydrophones are lowered over the ship's side so that the signals from the capsule can be monitored. If all is well, the position of the capsule is double-checked and noted before leaving the site. One month later, the ballast has been released and the float is sighted on the surface. The recording capsule is then hauled in from below the float and brought inboard. The capsule of the French Oceanological Center at Brest is developed from the first tide recorder ever put on the deep ocean floor in 1963. It backs off the main pressure of the ocean by compressed nitrogen contained in the cylinder on the capsule and records only the tidal variations by a vibrating wire sensor. This type of capsule doesn't release ballast itself, but is recovered via a separate release system at the end of a long rope. The rope is buoyed and may be dragged if the release fails. The shallow water capsule of the Canadian Marine Sciences Directorate uses a similar release system and also uses a backing pressure against the main column of water, supplied in this case from a rubber tube. The release float is held down by anchor chain. Finally, the recording capsule is lowered. Another shallow water capsule developed by the French Navy also uses the remote recovery system, but with a steel wire instead of a rope. A small acoustic pinger for location purposes is attached to the wire. And a string of pellets for the release float. The Institute of Oceanographic Sciences, Bidston Laboratory, prefer to avoid acoustic releases altogether and recover the capsule from a large permanent buoy and wire system. Their recording capsule is protected by a heavy steel cage. In this exercise, they included 4 different types of pressure sensor for instrumental comparison. The sphere contains a 20-channel data logger. The surface buoy has a flashing light and radar reflector. A very heavy chain at the end of the bottom wire from the capsule anchors the large surface buoy and keeps it on station. For initial testing, a cable from the capsule is retained at the surface to operate a typewriter which prints the recorded data for a time. All these operations of laying and recovering tidal capsules have to be accompanied by accurate navigation. The ship's own computer is used to plot the maneuvers by means of satellite fixes and electromagnetic log. Tidal recording also requires precision timing. A digital clock records Greenwich time to the nearest second. Finally, all the records obtained are taken back to the laboratory for analysis by complex computer programs. In this exercise, 10 separate records were successfully recovered. Their results proved to be in very close agreement. The working group coordinating the research on tides of the open sea are now confident that nearly all the methods tried were viable and accurate. With international collaboration, the way is now open to solving the long-standing problem in oceanography, the map of the ocean tides.